Now, without further ado, I'll pass this over to Armagon. Armagon?
Hi, good morning, everybody. Thank you so much, Odette. Hi, everybody. My name is Armagon Ibrahimi. I'm very excited to be presenting our third webinar of the webinar series today. And in this webinar, by the end of this webinar, you will learn how to use a tool from Sony NNC and how you can build your model on that. And then eventually you can port that model to Spresense and build your Edge AI application. I hope you find it helpful and informative. So basically, as always, let's cover some of the agenda items that we have in this presentation. I give you a brief introduction for those that they haven't been in our previous webinar to be able to continue and for this webinar with us. And then I will tell you about Sony Neural Network tool. And after that, we get to learn how to build a model using NNC and eventually port that on Spresense. So then you need to learn how to build your model, and all of the steps is going to be covered in that section. And then AI application on Spresense that has been developed with NNC, and we have some exciting announcements and news at the end of this presentation. So first, I would like to cover what is Spresense. Spresense is a development kit by Sony, and the significant or the most highlighted capabilities are Spresense has high resolution audio and also has the GPS or GNSS, which is Global Navigation Satellite System, integrated in it, and is covering almost everywhere in the world. And again, another significant things about Spresense is very low power. And Spresense has 6 ARM cores, which is with 156 megahertz of clock. And that makes it easy to target applications that they need to do a lot of processing. By the end of this presentation, you will get an idea of how to build the Edge AI application on Spresense. One of the highlights of Spresense that can support that idea is these 6 cores that we have. So you can do a lot of processing on the board and then less communication with the cloud. So it's going to be less expensive. And then also, because of low power, you can build your application, leave it somewhere that it doesn't have any access to power, and it does the processing for you. And basically, you can have a application. You can have your device running for a long time on a farm or any other places that it doesn't have access to any power. The exciting thing is we are going to have a new board, LTE board, that is going to complement our board, Spresense board, and it's going to give you the connectivity access, which is going to come up soon. And so now you have a good idea about Spresense. To just give you some physically, how does it look like? Spresense kit has three components right now. The middle one is main board, and then we have camera board and extension board. Main board by itself can perform, and then extension board and camera board is just complementary to make design and developing application easier. If you are interested to learn more about how you can find these boards and how you can order, please use the link that I have provided here. And of course, on our Spresense website, you can get even more information and details and spec about each of these boards. So to cover what we have done so far, as I mentioned, this is the third webinar. So we had 2 other webinars before. The first webinar, basically, this is just my agenda for the second webinar. What I covered there was summary of the webinar number 1, and then also I always do the brief introduction. But the main thing that we learned from the webinar number 2 was how to program Spresense with Arduino IDE, and then see for the features like camera, audio, GNSS, how can you program Spresense. So if you want to go back and look at any of our previous webinars, I have provided the link here. And after this webinar, when you get the recording, the slides is available also, so you can access those. Also is on our website. So first webinar was more like details and spec and why Spresense is low power, and we went deep down inside the silicon to show how Spresense is maintaining the low power. And then second is more programming Arduino, and then this new one that we have today is basically showing you how you can have Spresense and AI. If I wanted to give you an overview of the whole webinar that we have today, I should say that we go through 6 steps. So let's see what are these six steps that I need if I want to build Edge AI application. So the first thing that I need to do for any Edge AI application, I need to collect data. So before I go there, let me show you this. If you look at my screen, I have the Sony neural network console on my left-hand side, and then you see Spresense with a camera on the right-hand side. This could so now let's talk about this. So I have a first step, which is data gathering. You need to have some data images. If you want to build any AI application, you need some data set. So this is the first step. This step can be done by Spresense. So that's why you see the camera. For example, if you're targeting any application that you need to do some image recognition, you can take the picture with Spresense camera. First step is done. I collect my data, and now I need to build the model. To build a model, I go to NNC. And then for NNC, you need to go through these steps. You need to design your neural network. You need to train it, evaluate it. And then at the end, you will produce the model. And then by here, after you are done with NNC, you have a smart model that you need to port that model on Spresense. So this step is when Spresense get a model, and then the last step is when you do the recognition. So this webinar, this is the whole picture of this webinar, and we go through each step one by one. This is the runtime. This is the DNN runtime library. This is the deep neural network runtime library that is available by Spresense to support this model, and is available both for Arduino and Nutex. I don't know if you have noticed, this series that we had, it was more concentrating on Arduino, but for those user that they want to use Nutex, all these things is available in Nutex as well. So now let's talk about neural network console and see what it is. So neural network console is the tool that I'm using to build my model for Spresense. This is a Sony actually tool that we package with Spresense to target edge AI applications. It's very powerful, and also at the same time is very easy to use. So because AI concept is usually very complicated, and now we see that is in a lot of different fields, they somehow need to have some AI capability. They may be in different fields, but if they wanted to build any application, they need to know AI. So to make that easy for research, development, education, this tool is really good. At the same time, it's going to save a lot of time. And I tell you why. So let's go look at some of the features that NNC is providing. So for NNC, we have these 4 features are the main features that it makes it easy to use. You can do drag and drop for try and error. So I will go into each of these later, but just keep that in mind. So if you look at the picture here, is some boxes, colorful boxes that you see. And these are the functions and activation functions, mathematical functions, and multiplication, add, and everything that you need to do is in these boxes. You don't need to do a lot of programming, and you can just play with these boxes. And then this is the automatic. It can do automatic design search. So you design your network, and then you have so many cases, and then it helps you to pick and search among those. And then you can train and train and evaluate with click a button. Very easy. And then you can manage the history. Again, this is the website, so dl.sony.com. And I will tell you in my next sections how to go and build on this tool. So for now, let's just show you some of the highlights of this NNC. The first one was drag and drop. So this is a better picture that you see. We have different blocks, and then we need to put these blocks together to build our neural network. This is, if you don't have, this looks like Lego. You just put them together, and then if you are happy, then you can do optimization, and if you are happy, you are happy. Otherwise, you can play with these blocks and change the structure of your design. Usually in AI, this is what you do. You have to do a lot of coding. So here you can save a lot of time with coding, and you can save some time. And if you are not like deep down in data science, this may help you to start, and maybe you get interested and then use this tool. It helps you to build your own application. And then the other thing is automatic design search or a structure search. You have, if you look at this picture, you see a bunch of red dots here in this picture. What is happening is basically you do a lot of designs, and then you will see the data. For example, if I click on one of these, then I will see the architecture, I will see the performance, and then I can pick that. Or by just looking at this graph, we have the y-axis is the accuracy, and the x-axis is the computational complexity. It depends what is your target and what you need to achieve. And then you can think, okay, I will sacrifice some accuracy for the computation, or vice versa. So this is another one. And then the other capability is you can train and evaluate your design. If you look at this picture, I have the graph that is basically showing the progress of training. At the same time, on the right hand side, you see your network. So you are doing a lot of you are building your model, and then you want to see what is the how is it progressing. So you can, in real time, you can see how this model is progressing. Usually it takes a long time to build to train a model. So this is important. So we can go back and check, for example, what is the cost, what is the training error, what is the validation error, and this is visually available to you. And it shows you how training has progressed, and then you can get all this information. So now let's go to managing your training history. This is another good feature. If you look at this side, which is my left-hand side, is all the history, means all these are all the models that you have built, right? And then when you look at the middle part, this is the result table. And then at the last section on the right-hand side, you can preview the structure. So now you have done your trainings, and then you just want to, and you did the evaluation. You just want to know which one is the best for your application. You can easily click on it, and then you will see all the data, and then you will see the results in a table. And also you can look at your model. For example, this model with all these blocks is doing a good performance or not. So in this these are the 4 features that is good to mention, because then you can basically avoid intensive coding or time, you can manage your time better with this tool. It seems very simple. I will show you some more example that you will find it even more easy. What I've provided here for you is to just give it a try. How this is, we have examples available. If you go to this link that I provided here, you will get a sample project, and basically you can go through these steps, which is you have to start the neural network console, and then basically you open the sample project, you view the content of the sample project, and then you do training and evaluation. This is only 5 steps, but by the end of this, you get a good feeling of how to use this tool and how simple and easy this tool is. So that's what I suggest. So for the first, you can start with that. Also, to just finish this section, I would like to mention that we have a YouTube channel with a lot of videos for users to learn how to use neural network console. Currently, you see a lot of those being in Japanese, but our team is putting up a new playlist in English, which is gonna come out by the end of this month, which is not that far, right? So please check that out and see how you can take advantage of simplicity and capabilities that neural network console has. So we are done with just giving you a brief overview of neural network console. The next step is to use it and do these things. What we do first, before we start with neural network console, I will give you some basics of neural network console. So you will learn some concepts that is popular in neural network. And then after that, we prepare our environment to for neural network and download it, and I'll tell you about the steps. And then we have to design a neural network, and eventually we have to port it on Spresense to build our Edge AI application. To start with the basics, it's good to know this few things. I assume that whoever is on this call had some little bit of background in tech engineering, but data science is a very vast topic. I mean, I am not the expert in this, but to make it easy for you to understand the steps, I just go over some of the concept to cover the basis for neural network, and then we can build our model. With this knowledge is enough for you. And if you want to dig into it more, there are a lot of good references, books out there that you can go and build your knowledge. And if you're expert, good for you. I have to learn from you. So first of all, this is the big picture. When you look at a deep neural network, what does it mean? So deep neural network is basically, think about this like a brain, and then you have neurons in this brain. And then the way that neurons communicate, they send some messages to each other. And if this message doesn't get to the right neuron, and then for example, if you're looking at something, you don't see it. Or think about it like a brain of a child. When at the beginning they can't talk, they don't know some of the objects or animals, and then gradually they learn. So when we say neural network, think about it like this is a computer version of human brain. So here I provided some example to just give you an idea of what is happening if you want to build Edge AI application. I start from left-hand side. So I have some training data. So training data here, I am trying to recognize if the picture is a flower or if is an elephant. And then this training data is a bunch of pictures. And this bunch of pictures goes to a tool, which here we are using NNC. And then at the end, this tool will generate a model for you. So this model eventually should go on a microcontroller like Spresense. And then on the Spresense, when you put this model, means you have an engine, which is smart, and it can recognize if this is a flower or if it is an elephant. So when you feed a new data, as here is a flower, then Spresense use this model, does the inference, and then it tells you this is a flower. So these are the two steps that you see up here. Now let's go inside the brain, inside the training, and see why, what is happening inside the brain. For this one, I have the flower going. So this is, this is the input data, and the output supposed to tell you this is a flower. What I have in the middle is the neural network. Neural network, think about it like the brain. We have a bunch of input, means I'm looking outside, or I'm just trying to recognize something. And then at the end, I will get some output. Here, so input I, output O. In the middle, we have H1 and H2. So these are, they call it hidden layer, middle layer, however you call it. There are different terms, but it's nothing but what is happening inside this neural network. And then I have W1, W2. These are the weights. So this means when I have this input, for example, if I want to go to the next one, means two neurons that are connecting to each other, there is a weight. And if this weight is here, as far as mathematical function, basically you multiply this input to this weight, and you add some value, some random value, and then you go to the next layer. You go through this neural network. Here I have only 2 layers, so many times until your model is your model achieves what you need to achieve. I don't want to say perfect, because nothing can be like our brain. We are trying to build a model to work like our brain, but eventually, whatever that is, here you need to recognize a flower. For example, if you are training a robot, at the beginning, you see the arms and legs are going to so many directions, and at the end, you will see that it will move. The robot start moving correctly, and this is when we need to do the training, and this is when it takes time. And there are other factors here, like the training data is important, how many layers you put here is important, which we go to detail a little bit more in the next slides. To simplify that, now you have a good idea of what we are doing for neural network. Let's see how we graphically can explain it. We have on the left-hand side, we have the input layer, output layer. You learned this from the previous one. And then here is middle layer, hidden layer, whatever in the middle, which you do the training. This thing is the same as what you see, the colorful blocks on the right-hand side. This is how we work with NNC and build our neural network. The first one is, and by the way, everything is color-coded. So the first one is your input. So this is your data set. And then the last one is your output. In the middle, this is your middle layer. And then we have different mathematical functions. So here, when you see blue is the mathematical function to do the matrix multiplication plus some value, random value. And then tan or sigmoid, these are the activation functions. And then the activation function is basically converging the input to some value that is more easier to use. So I will talk about those later on. But then you see some numbers on the right-hand side. For example, the input for this structure that you see here is 28 by 28 picture, and the output supposed to be 1 digit. So it is, the output is 1 output. You will see 1 output. Here is 1 output too. And then for affine layer, you have 100 input, and then same goes to 10. And then at the last level, it's going to be 1 input and then 1 output, and then you see 1 output for the binary cross entropy. So this is just to give you the overview. I will go through this in more detail in the next slide. And by the end of this section, you have a good feeling of about each of these blocks. Okay. So now let's show you an example. What is this? So I have number 9. So we are trying to do a recognition of handwritten digit 9. This is a picture of 9. which is acting as our input, is 28 by 28, which is going to be 784 pixels. And then the output, I'm going to get 10 outputs, because we can get 0, 1, 2, or we can get, if it's 9, means that's the output that was recognized by this. Here you will go through different layers. Here we have 3 layers. We have 3, so you see the different colors, right? So we have actually 1, 2, 3, and then the last one is the output. It goes to the output. So for this one, basically this 200, this is 784 input, and then you pick the output 1000. There is no, oh, I did. Okay, sorry about that. So for this one, we picked 1000. This 1000 is, it doesn't have any rule. Here I picked 1000. You can pick something else, but some other numbers. But this is how you design. So your FN and TAN, you will get the first layer 1000, and then the next one is 300, and then you get 100, and then at the end you get 10. And then between, so TAN is the activation function. I will tell you a little bit more. And then softmax is what we use for the output activation that for this design. Let's see what is affine and what is TAN. When we say affine is nothing but fully connected layer. What is fully connected layer? Means you have whatever input you have, it has to be connected to all of the outputs. So here I have 784 input, and my output is 1000. So it means that I have 784,000 parameters, because I need to connect each of this input to the output. And then what was TAN? TAN, I told you, this is the activation function. Activation function is doing the basically is converging the input value to the range of -1 to 1. So basically you have this layer, and then you need to converge it to a certain range to be able to process it. And this is why we use the activation function. For here, tan h is between -1 and 1. You know, you learn what is affine, what is TAN. Now let's look at this, the next slide. What I have here, this is the convolution-based neural network. The first one that I show you was, let me go back, then it was affine based, right? So what is convolution? Usually for the pictures and for the images, we don't use affine. It's not popular. We use convolution. Why we use convolution? Because we want to improve the performance. And how we are improving the performance, you can see in this picture. So you have the number 9. Instead of connecting all of the inputs to the output, which was a very big, large array of parameters, so what we do, we apply some filter at the first level to this number 9. Filter is nothing but, like, I guess everybody's using their smartphones, and you have a picture, you apply a filter, it makes it more, you know, it sharpen the picture or blur the picture or change the color. So those are just same concept here. So you apply different filters. So here we have 6 filters. At the same time, we pick a 5 by 5 pixel here, and then this 5 by 5 is going to be connected to 1 pixel in the next one. So when you look at, when you do the calculation, means basically this when convolution happens, this 5 by 5 moves to the, if you look at this corner, it moves toward the other direction, and every time it moves by 1, and then at the end you will have a 24 by 24 picture. So what we did, we had a 28 by 28 picture, and then we picked a 5 by 5 a filter, and then we pass that filter over this input, over this picture, and then we generated 6 picture, but this time it's 24 by 24. There is another technique that we use in image processing that they call it max pooling. Max pooling is nothing by dividing this height and width by half, for example. There are different type of max poolings. So here is you pick the maximum number in, for example, a corner, and then you pass that one to the next level. So here, what I've done, so this is again 6 filter stays the same, and then I divide the height and width by 24 divided by 2 is 12. So by here, you see I pair up the convolution and max pooling together. And now I have a 12 by 12 pixel picture, and I have 6 filters. So now the picture is smaller, right? And then again, I apply another layer of convolution and max pooling to get to the point that I have 4 by 4 by 16. So next one, again, I apply, this time I have how many filters? First one was 6. This one is 16. So I have 16 filters, means more. And then you see the size, the image is going to be 8 by 8. And then again, we apply the max pooling, which is going to divide the height and width. So it's going to be 4 by 4 and 16. And in the last layer, you see that we apply the affine and tan. And then after that, we have 120 output. And this 120 goes to, again, another layer are affine and softmax. Softmax is your output. And then what you do, you generate only 10 outputs. So you see, this is an example of convolution based network, usually for image processing. And in the next slide, I will compare these two side by side. And then I tell you why we maybe now is more clear after we did 2 try with 2 different type of network, and see which one is better. So when we say affine, we said this is fully connected, means all of the inputs are connected to outputs. If I have 784 inputs and then I have 1000, then this is 784 multiplied by 1000 is going to be 784,000 parameters, right? But in this way, I have only 150 parameters. This means less memory, less calculations, right? So this is important when we do convolution. Basically, the way that we do it, we had 6 filters and we had a 5 by 5 kernel, which is 25. 25 multiplied by 6 is 150 parameters. This is the way that we do image processing, is a technique, and it is helping us to improve the performance. You have learned 2 type of design for neural network, and you understand affine and you understand convolution now. Now let's go and see how we can build a single unit or just one unit. If I want to build a network with one unit, what should I do? On the left-hand side, you have the affine, and then right-hand side is convolution. By now, you should be able to tell me affine or convolution, what does it mean, right? So for the affine, I have one affine, and I can apply an activation function to that, which is tan. And I told you tan is just converging the data between a range, and it could be we can use any kind of activation that we want. But here, as one unit, I have used affine and tan edge. And then for the convolution, we have convolution, which is the blue box on top. And then I have activation function, which is another tan edge. But in the middle, which I can, this is optional, we can do max pooling as well to do downsampling. So usually when you look at the unit for affine, you can have affine with activation, and then for convolution, you have a convolution with activation. Max pooling is just to improve the performance for downsampling. These are your basic units. You know your input is black, so all these are color coded. And what you need to decide is what is the output. To pick the output means it depends what are you designing. If you are designing a binary classification, you need to pick sigmoid. If you are designing a category classification, you need to pick softmax. And also for regression analysis, there is no activation. You are just applying the squared error. So this is the last levels, because we said we have input, we have middle layer, we have the output. Output usually gets designed by developer based on what they need to get. But basically, you divide it by these 3 different categories. If binary, so if you want to get, if you expect to get something that is 0 or 1, this is your binary classification. If you are looking at a category, like you want to see the female or male category, for example, you can use this one. And then for the regression is when is a continuous value and there is no activation. So by now we covered all of the bases and data structure that you can build with neural network. You are familiar with the building blocks, and I'm going to the next one. I'm sorry. So here now, after we learn all of those basic blocks, let's do a preparation for our AI and see what we need. What we need is only 3 steps. This section is very simple to just tell you where you get your tool, how to prepare your data, and basically how to transfer that data to NNC. Very simple. So first one is where you can get the tool. For example, here I select the tool that I'm sorry guys. So this is you go to dlsony.com. Here is the neural network console. You can download it. This tool is free, available to everybody everywhere. And the cloud version, if you have a Google account, you can use the cloud version. And then what you need to make sure that you have enough disk space available on your device or on your computer. And then if you have the CUDA enabled NVIDIA GPU is going to give you a better performance when you do the design unit for an evaluation and train and everything, but that's optional. If you don't have that, that's fine, perfectly fine too. Next step, so now you know where to get the tool. You need to prepare your data set. For training, we need 2 sets of data. We need the training data and validation data. And that makes sense, right? When you have the training data, means I have to train my network to be able to recognize something, for example, between cat and dog. And then if I'm doing the validation data, then I need to validate after I train, I need to validate. So I need a set of data. Can I use the same training data, validation data? Probably that's not a good idea, because if I'm training, I want to challenge my network to see if it can recognize something that was not in my training data. Or for example, if I'm training between cat and dogs, if I just include all cat pictures in my validation, then that's not a good sample. These are all there's a whole science behind this collecting this data, and how many data, if it's larger, of course it's better, but do we have a space and all of those. But for now, just think about it. I need 2 sets. I need the training data, validation data. Here we are doing digit handwritten or digit recognition. This is not handwritten. So digit recognition. And for that, we have 2 sets for training and for validation. And after you have that, you need to go to the tool, you open the NNC, and then you go through these 3 steps to bring that data set to NNC and start building your neural network. So the steps are, first you need to open it, and then second, when you open it, gives you all of the CSV files, and at the end you can import it. For those of you, if you want to build your data set, is fine. Otherwise, you see this numbers that underscore dataset.zip. I will provide with after we are done with this, with the recording, all the slides and all of this code and data for you. So then if you want to start, it's going to make it easy to start with. Or you can build your own. Or there are a lot of classic examples for data sets that you can use from online. So that is, to start with, is very good. So we are done. We are now ready to go to the next step, which is designing our neural network. For designing our neural network in this section, we need to go over how we can build a single unit, double unit, and then convolution neural network, and then at the end we need to optimize it. In this section, basically we go step by step to see how we can build a model to recognize between 4 and 9, and we want to recognize 9. So we are just, if it's 9 is 1. So let's see now. You know about the color. So I have input always black. I have the last layer is gray, which is my output. And then here in the middle, the blue one is affine, and then sigmoid is my activation for the output that I'm applying here. Let's see what is going on here. I have a 28 by 28 pixel picture. I need to generate one output. And then basically for affine sigmoid, I have one input, and then at the end I see one output. Let's look at the picture on the right corner of this slide, and let's see what's happening inside. You have 4 and 9, and then this is going to be your input. So basically it's 28 by 28, and then you go through this step. First is affine, means affine is 1, means I have to connect all of the input to one output, which I have on affine. And then I have to apply this sigmoid, which is nothing but applying this applying this activation function. And then I see the output, which is going to generate 0 or 1. So sigmoid is the output layer, and then is converging all of the outputs if it's 0 or 1. So if something is 100%, or if 0% or something in the middle. This is for the designing a single unit. You see how simple it is? This is a Legos putting them together. This is your single level. You can put 2 of this together, then you're gonna have double layer. Or let's go to the next one and see what we are doing. So basically we are adding another affine layer here, right? So I have the input for a 9 again, it goes to affine, and this time my affine has 100 output. So I have 784 goes to 100, and then from there I apply the tan edge activation. This is one layer, and then at the end I have another affine, and sigmoid is for output again. So you see I have 2 layers. This is just putting 2 affine type of structure like together, neural network. And then for the next one, we just wanted to add some convolution. This is an image. Let's add that. Here we had these 2 layers before, and then I need to add the convolution layer. You see it in the red box, and then convolution is basically 24 by 24, and the output is 4. You apply max pooling, and then this is another activation that is called ReLU. This is another type of activation that we apply here. So we have 2 level of convolution. We just add it here, straightforward. So now I have added more layers. As you see in NNC, you can play with this thing and then basically build your model and see the performance and see if you're happy or not. By now, I have designed my network, and now I want to look at some of the accuracy and average precision and file size for the memory, and see which model is the best one to use. If you look at here, basically is I have added another layer, which is when you don't have enough data samples or data set, you apply this image augmentation layer and also random shift. This is nothing but you are resizing, doing distortion at random, and also you do image shift at random. So basically, to make your model, you play with the pictures and you generate more data to be able to do a better job for your neural network and generate a better result. And the rest is the same. I forgot to tell you something. So when you play with all of these blocks and you put them back and forth and you remove and you add different, I want to tell you this, all of these parameters that you see here, they are adjusted by the tool, which is a great help, big help. And then you know that this is is happening and is right. So this is my design, and this is a convolution network. What is important for us at the end of the day when we design a neural network is what is the accuracy? So here is 99.5%. Average precision is 99.5%, which is, wow, that's good. And then the file size is going to be 416 kilobyte. So this is the file size, this is the memory. Usually when you use any microcontroller, you don't have unlimited memory. You have limited memory. So it's important to see how you can play with your model and reduce this memory size. At the same time, keep the accuracy and precision good enough for your design. And NNC makes it easy, of course, to play with that. If you see in this design, I have removed some of those blocks, and here maybe I have only one convolution, and some of the activations are different, adjusted parameters right here. And now I have the accuracy of 98.9%, and then the precision of 98.9%, which is not that bad compared to the previous one, but the file size is 148 kilobyte. So the first one was 416 with 99. The second one, with removing the convolution and just having one layer of convolution, is giving you 148 kilobyte and 98.9. Let's go and play with this again and change and remove and some of the layers again. So this is gonna be only, you have a convolution layer and max pooling, and you have the affine layer here. And what you get is 97.8%, and for accuracy and precision. And the file size is only 14 kilobyte. How beautiful is that? This is really good, right? So the memory, you reduce the size. If I go back, we started with 416, and now we have only 14 kilobyte. So imagine every time you do any type of design, you need to let this run and train, and takes a while. But with all just, changing these blocks, moving these blocks around, at least you can take care of the design very quickly, and then let it be. And then all this information is available through GUI using NNC. So in one glance, you can just see what is happening or how this is progressing, and if you want to continue, or if you're happy with it, to keep it. So you can go through your history and pick the right one and apply that. At the end of the section, I'm providing an example for you to try. So this is just a simple neural network that it has all of these different middle layers that we talked about. It has affine, it has all of this convolution, max pooling. Just play with this and see how you can improve the accuracy and precision, and also play with the memory size and see how you can change that. So now we know how to build and design a neural network, and I guess we are more comfortable with NNC. Let's go to the next step, which is how we can port the model to Spresense. By now, you have designed your model and you want to put it on a Spresense microcontroller to build your Edge AI application. So we are going through these steps here. First, we need to, the model that we train has to be transferred to Spresense. And then I tell you a little bit about what is the library that supports this neural network. And then I show you some code in Arduino. And at the end of this section, I will tell you, show you some of the real examples that has been done with Spresense and with Spresense and with neural network console. So this is very easy. After you go through only 3 steps, very simple. You finish your design, and then you need to do export. If you see in my picture on the left hand side, you need to export the model. For the exporting the model to Spresense, you select NNB, and you may hear Nabla here and there. That's our neural network library that we use to support the neural network. So here you see Nabla C runtime file format, and then you generate this file format because Spresense understand that. And then this model is going to be modeled, and the extension is NNB, of course, and then you put this on Spresense. Here I show that it goes to the SD card, but this model can perfectly sit on the main board also, just for simplicity. Here is your model on the SD card, and we go to the next step, which is telling you how you can write the code. This is all the code that you need to do the recognition for that for number 9. And let me tell you different. Let me tell you what is needed in this code. First, you need to include the library, which is DNNRT. So deep neural network runtime library, that it needs to be included means I'm dealing with neural network. And then you need to instantiate a variable from this DNNRT, which is here is DNNRT. Of course, we are accessing the SD card for this example, so I add the SD card. And the next step, you need to open the SD card and read your model. And for that, when you say dnnrt.begin, means you are starting and beginning to get this file to this DNNRT using this dnnrt.begin. And then after that, you need to feed an image, because I told you, so you build your model and everything. Now I have a device, I have to say, this is my image. So this is a number for .pgm. So this is the format of portable grayscale map, but you can use different type of formats as well. But here, this is the format that I have. This is my picture to see if my Spresense can recognize this. After that, we have a variable. So when you look at DNNRT, there are two main things. One is the library that we mentioned at the beginning. So it's DNNRT, that library. And the other one is DNNRT variable that we use it for basically data input output. So I'm using this variable to get, I'm telling what is the width and what is the height. So here we have a 28 by 28 picture. So you need to give that to the variable for DNNRT. And then you have your buffer. Your buffer is going to get this picture. You do some normalization here, because we have it depends what kind of normalization you are using, but here we are basically using this normalization for this neural network. This is that part. And then the next level, if you look at the last block or last box, it's going to show you how to do the inference. Means now I have my input, and then I go to my smart engine to be able to recognize, and then at the end I do show the output. Last part is nothing but just printing out the data. This is all you need to recognize this number 9 digit. I have provided a link here. This link has this information in our documentation. This code is available in the example folder of SDK and it's DNNRT. If you want to give it a try, then you can refer to this webinar and also the documentation here to try it for yourself. So as simple as that, we are done with DNNRT, and then we just have it on Spresense. I'm going to show you an example of basically how to read these numbers with Spresense. I have added the LCD here. We have the camera. How to program LCD and camera is in my previous webinar number 2. But here we are concentrating on the DNNRT. So this example is, first of all, it is using some grids to adjust these numbers in these grids. And the blue one that you see up here means Spresense recognize this number as 0, 1, 2, 3, 4. So what we do, we have a button here. We point the camera to this grid, and then take a picture, and then Spresense does the inference and recognizes this blue number, and if it's matching, means it did a good job. If you want to do that programming, the first part is to just building this grid and make sure the numbers are in the right place. This is simple, just programming and telling you what is the box width and height and all of those. And the next one is just the code to get your NNB model, of course. And this model it can recognize between 0 and 9. The previous one only recognized 9. So this is the code for, this is the model for that. And I will provide all of this for you. And this is the code. This is, again, you press the button and then it goes through the different steps to set the input data, and then you do the inference, and at the end you can do the you can look at you can see the output. So this is all the code that you need to build this application. And if I want to, at the end, this is the output. So this is the number that I see, 0, 1, 2, 3, 4, and then the blue one is what Spresense recognizes. Have you noticed this is just a simple smart meter reader that nowadays is very popular among utility companies to recognize, to do the meter reading. Instead of sending people around the houses, you can have a camera and just do this recognition. This can be applied to any other applications that you need to read some data in this format, for example. So this is easily a very popular application that you can build. So for how am I doing with the time? Okay. So for this one, I have provided. This is a very interesting example. You can build a smart camera, AI camera with Spresense. You can recognize if it's what kind of image. So is this a human? Is a horse? Is a rabbit? Whatever it is. And then in this video, it's only 2 minutes. You can see how this has how it works and how we built this. And let me just go back. So try this when you get the slides. And then I have provided a bonus slide for you. This is, I told you at the beginning of this the section that you can take some pictures if you want to build your data sets. You can build some pictures using a Spresense camera. To use a Spresense camera, basically, you can use this code to build that data set. So give this a try as well. I have to go a little bit faster. So for the last section, these are just some examples that that we use Spresense with NNC to build some real life applications. For edge computing, you can target farming, agriculture, industry 4.0. You can do a smart city. The sky is the limit. It depends what type of application. Anything edge AI, Spresense has 6 ARM cores can support that. But here there are some samples, some examples that we have done. So the first one is the license plate recognition that in this example that you see. For example, I have 2 sets of data, so I have to be able to recognize a car, and it's not a field, so it's a car. This thing that you see here does that recognition to see if it's a car, and then the next level it tells you what is the license plate. So you see all of these blocks, and you see this is the design. This is a neural network designed for this, and at the end, Spresense is doing the calculation and inference, and it does the recognition. We use edge computing because whenever we communicate with the cloud, that means it's expensive. But if you can do all of this computation on the device, and then whenever you need to communicate with the cloud, access the cloud, is gonna help you with that. So this is one example. The other example is rock, scissors, paper. This is to recognize the gesture of your hand, if it's a rock or scissor or paper. And this example, I have shown it in so many events, is amazing. It takes only 0.07 second to do a recognition, so it's pretty fast. Or 6 ARM cores, so the Spresense can do that. And the next example is it could be a good example for agriculture. You have a field of tomato, and then basically you need to do the recognition of find the tomato first, and after you find the tomato, you need to see if the tomato is ripe or not. And this is example for that. I have to go a little bit quickly, sorry guys. And then the last one is the previous one, they were covering the camera, so I use the camera for doing the sensing. Here I have the accelerometer and gyroscope to detect the movement of my my hand, so it can go in circle, screw, or no movement or twist. So this is another example. Again, you can target agriculture, you can target smart city, you can target industry 4.0, any edge computing with a smart engine Spresense can handle, and it is low power. So let's wrap up and tell you about the upcoming news. The exciting thing that is happening, our LTE board, which is very popular, even not coming out, is still, even though it's not out yet, is coming out by the end of this year. So if you want to learn more, please go to our news and webinars. And also, if you want to do any kind of communication with us, if you want to put any request, then please use this link here. By the way, in my previous slides, I provided a link for forum. So when you do your design and if you have any questions, you can always communicate with us via our forum, and we try to get back to you and help you with that. So I'm concluding my presentation here. Thank you so much for being here. I hope you find it helpful. Spresense is an edge computing device, very low power, and we can target different type of applications with Spresense. So now I'm gonna transfer this to Odette.
Okay, thank you so much, Armagon, for such an informative presentation. And thank you for all who have stayed with us throughout the webinar. We do appreciate you staying throughout all three that we've done this year. And just a quick question, if you haven't submitted your questions yet, please do so by typing them in the question section on your GoToWebinar platform, and we'll get to them. We do have quite a few that we have to get to today, and I do have to be aware of the time that we're here. So I'll try and get to probably the top 5 first, and then work my way into the others. So Armagon and Camille, the first question that I have on here is, what machine learning platforms does Spresense support?
I can answer that. So currently we have package Spresense with NNC from Sony, and we are working with popular tools out there to make them possible on Spresense as well. So that is the current situation, but we will have some good news coming up soon.
Okay, perfect. The second question that we have is, what is the maximum size of your neural network model that you can use?
Okay, I can take this one. So this is around 1 mega. It depends on the size of the application, because this process has only 1.5 megabyte of RAM, and you need to fit your application and model there.
Okay. Okay. The third one that I have is the NNC page says for Windows app, this application is currently available for downloads only in Japan. Is that correct?
So this is actually, you can, it's 2 versions, is Windows version and cloud version. For the Windows version is available everywhere. For cloud version, if you have a Google account, you can definitely download it and use it.
Okay. Hope that's that's what they're looking for. The other one that I have is, can I only use the main board, or do I need the extension board to port my AI model? This is a very good question.
I can take this one. So you can use only the main board if the model is in the flash memory. So you can do this, but it's much easier to use the SD card and have the model on the SD card, but then you need to use the extension board.
Okay. I have 2 more that I'll get to right now, as I said, we're running time-wise. Is there any GPU acceleration available for the NNC?
Yes, it is. There is a still CUDA support.
Okay. And then the last one that I have is, are there any API besides the GUI tool?
Yes, there's a Python API that you can use.
Okay, perfect. Thank you so much for answering those questions, Camille and Armagon.